Okay, we're going to go over transforming sinusoidal functions, and specifically, we're looking at this relationship, y is equal to sine x. And what we have down here is similar to on your quiz. This is a few periods of the function y equals sine x. Okay. Now, what we're going to do is we're going to go over transforming this, and I want to relate this to quadratics because we've actually transformed quadratics before. Does anyone know what the basic of a quadratic looks like? So what would the most basic form of a quadratic? Y equals what? What value? No, that's linear. Does anyone recall this? That's just that. That's the most basic form. And the most basic form, if you guys remember, goes through here. And when we talk about translating it or transforming it, we talk about moving this specific one. This is the one we're in reference to. We move it right, we move it left, up, down, or we stretch it, or we compress it, right? And when we do that, it's usually in what's known as the vertex form of a quadratic. Does anyone remember the variables for the vertex form? Y equals A, yeah. That's right, x minus h squared. Perfect. Yeah. This is identical to transforming a sine wave. The only difference, instead of having squared, we have the function of the sine. So our transformation of this function is written as y is equal to a sine x. Now technically it's sine bracket x. What goes in the bracket? Minus h squared is a quadratic, and then plus k. So the difference between the two is a quadratic, if you guys remember, is always when the variable is squared. A sine wave or a sinusoidal function is when we have the function sine. So all of these things do the exact same stuff as our quadratic. So let's talk about k. What does k do to a quadratic? Defines the y. What does it do to the whole function? How would you describe that? It moves it up and down. It moves the entire function up and down, right? So if I were to give a value of plus 5 to this, it would go up 5. So I would take each of these coordinates and I move them up 5 units, so it'd be way up here, right? It would be a 5-unit shift. If I were to make it negative 2, the entire function would go down 2 units. And we can be very exact with this. I'm going to bring up Desmos. Okay. So if you guys recall, here's our sine x. There's our wave. It's technically in radians, I think, right now, so I'm going to change that. Give me 1 sec. There it is. I want this to be in degrees. We'll zoom out. Sorry, I should have set this up a little better last time. Oh, you can't see it very well. I gotta set better parameters. X between, and then the y will be between 3 and negative 3. There we go. Okay, so there's our sine wave, right? It crosses at 180 as a peak at 90. This is all in degrees. If I were to put negative 2 at the end of this, we would have the same sine wave, but it'd be shifted down 2 units. If we were to add 5 to this, so I have plus 5. Oh, sorry, that's equals plus 5. It is now shifted up 5 units. And I guess I could zoom out a little. Get a better view of that. Okay? So these are all transformations of sine x. That's what our k value stands for. So let's go back. What did our h value do in a quadratic? Yeah, horizontal shifts left and right. Okay. Now with k, if it was positive, it went up, and if it was negative, it went down. What happens with our h? Yeah, it's the opposite of what we're used to seeing. So let's go back to decimals again. And this time, if you guys notice, because we're in degrees, we have to make relatively large shifts. So I'm going to hide these two here. So we're just looking at the regular one again. Zoom in. Oops, I ruined it. Oh, guys, I'm sorry. Sorry, we fixed that. All right, so we take this sine and we put in brackets x, and if I say plus 90 degrees, which way should it shift? It should shift to the left 90 degrees. If we notice, remember our original high point is at 1 and 90 for our sine wave. When we shift it left, this point has shifted left 90 degrees. So that 1 value is now at 0. It's gone from 90 to 0. Let's say I were to shift it sine bracket, we'll say minus 45 degrees. We should probably get x in there. Thank you. This has shifted 45 degrees to the right, that same major point. And if you want, you can look at x-intercepts with that same idea. This one is shifted to the left, this one is shifted to the right. Now, I want to show you guys something interesting about these. I think very annoying. What if I decide to shift this 360 degrees? What's going to happen? Anyone know? It's the same thing as what? Our sine x. If we take away our sine x and then turn it back on, it's the exact same thing. And that's because what? How long does a cycle take? A period. It takes 360 degrees, right? So if we were to shift to 360 degrees, this point has technically moved all the way over to 360 here, but it ends up being the same pattern because this pattern repeats forever. Okay, so this is actually giving us the exact same thing. And finally, what did our A do? Does anyone remember? Yeah, it told us if it was upwards or downwards. So if it was negative, it told us if it was facing upwards or downwards. And if it was greater than 1 RA, yeah, stretched. And if it was between 0 and 1, it's compressed. So that same idea happens with our sine waves also. It's not so straight. Oh, I'm just going to move these out of the way. Okay. So we have our sine. We'll move this one out of the way here. If we were to give it a negative sign, so negative sine x, if you notice, it's been flipped. All of these major points have now been flipped upside down. They're flipped on the equation of the axis. Okay, we've inverted it. So instead of going upwards, it heads downwards from 0 and then comes back up. The period's still the same, but our points have changed because it's negative. Okay, let's turn that one off for a second. What if sine x, I give it a value of 2. We'll give it our value of 2 here. And if you guys notice, I'll zoom out a bit, it's now been stretched. Now, it's still crossing the x-axis at the exact same points, but our high point at 90 and 1 is now at 90 and 2. So the amplitude has doubled. Okay? In fact, whatever our A value is, that is the amplitude of the wave. So normally in a sine wave, A is 1, our amplitude is 1. With our sine wave here, we've given it a value of 2. If I change that to 3, oh my gosh. Well, not 32, that's a little too high. If we change it to 3, you'll see it's been stretched even farther. Its high point is 3, and its low point is negative 3. And finally, if we were to compress this, we need a value that's between 0 and 1. So let's go 0.5 sine x. And if you notice, it's compressed. It's like something is squishing it. So the high point is now at 0.5 instead of 1. It's essentially the amplitude of the function. And we can put all of these together to shift it left, right, up, and down at the exact same time. It all ends up being the same thing.